Hello everyone, welcome to today's second day of our lecture series, and today we have Professor Ueda with us to deliver a lecture on tectonics of Japanese islands. So I welcome him to this lecture series, and his major area of expertise is tectonics. So I am handing over to Professor Satish Kumar to say a few words about Professor Vedas.
Okay. So good afternoon, everyone. So as Adira has explained, Professor Ueda will be giving a lecture on subduction and accretionary tectonics on Japanese islands. I think it's better that Professor Ueda introduce himself. He is a well-known geologist in Japan, so he is going to give you a very good explanation on the Japanese tectonics of Japanese islands. So please, Ueda-san.
Hi. Nice to meet you. I'm Hayato Ueda. As Jan and Satish-san introduced me, I'm studying about tectonics, especially on the subduction zones. So sometimes I study about accretionary complex and sometimes high pressure metamorphic rocks. And today I'm going to focus on the accretionary complex in Japanese island. Actually, I'm not good at speaking and hearing English. And this is the first time for me to have a lecture in English. So I'm a little bit nervous and I'm not sure if I can do or not, but I will try. And first of all, I like to know the educational background of participants because I don't know the grade of you all. Probably a mixture of undergraduate and graduated students. So here now I'd like to ask undergraduate students to raise your hand if you can. 伝わってるかな。ああ。increasing. 大学生。Okay, thank you. Oh. So the next, the graduate students, please raise your hand. Master course, please. Okay, probably half and half, I think. And the rest may be elder people. Okay, thank you very much. So, okay. And here I'm going to begin my talk. If you have some question, please write your question on chat. And not always, but sometimes I will check the chat. And if I find some questions, I will answer as possible. Okay. So today I'm talk about accretionary tectonics. And here I presented the contents of my talk 1 to 4. And from 1 to 3, this is the basics of the accretionary geology. And the fourth point is to talk about the I will talk about the geology of Japan, but I'm not sure if I can reach to the fourth topic within the given time of 1.5 hours. Okay, so let's start. First, I talk about the concept of accretion. So in geology, and usually we use the term accretion in probably two major meanings. One is tectonic accretion. This is the main theme of this main topic of this talk. But there's another accretion of common sense with magmatic accretion. And in the case of magmatic accretion, the magma or igneous rocks are accreted, and they come from the mantle upward towards the overlying crust. So the direction of the accretion is upward, and the crust is thickening vertically. And in the case of tectonic accretion, in the sense of subduction zone tectonics, the materials are oceanic crust or sediment rested upon the oceanic crust. And they come from the subducting oceanic plate. This is the lower plate. And the material accretes to the continental crust or upper plate. That is the hanging wall. Okay. Hanging wall of the subduction zone. And the direction of accretion is, this is not correct, from oceanward to continental ward, and the direction of growth is oceanward. Okay. And today's talk is just focused on tectonic accretion and not about magmatic accretion. Okay. And this picture shows the basic concept of tectonic accretion in the subduction zone. Please look at the upper panel. Here, the green is the oceanic crust that is subducting beneath the continental crust. And oceanic crustal rocks or sediments are moving together with the underlying oceanic crust. But when the oceanic crust subducts, not all of the sediments can subduct together with the ocean crust, and some are peeled off or scraped off and attached to the leading edge of the upper plate. So we call it as an accretionary prism, or fukatai in Japanese. So in this case, the sediments on the oceanic plate are accreted to the continental crust. Okay. And this process is analogous to an accident of belt conveyor in the cake factory. In the lower panel, the belt conveyor is always moving and carrying sediments or cake. And if there is some backstop that obstruct the sediments to subduct, so the sediments are attached onto the edge of the backstop. So this is the accretionary prism. So this basic concept can be confirmed by experiments. So next slide, I can show you the case of experiment. This is very simple equipment to in order to look at the process of actual accretion, and we call a sandbox. And this box was made by one of my students in 10 years before something. And this box is walled by glass in both sides, and there are some slit at the bottom of the what to say longitudinal side, and there is a wooden board that play a role of oceanic plate, like the picture of this, and sand is deposited manually by hand, and there is a backstop plate that is analogous to a continental margin, and one have to push this backstop, and the other one move the underlying wooden board to this direction. So the sand deposited on the wooden board wants to move together with the wooden board or oceanic plate, but backstop obstruct to move. And so the moving sand are attached to the wall of the backstop, and we can see the growth of accretionary complex here. Okay. So let's do the go to the movie. So yeah, I will start the movie, but before that, please check the point of view. So please look at 3 points. The first, there will be some thrust faults and fold created, and these are progressively formed. And so please look at the how the fold and thrust fault propagate as the oceanic plate subducts. This is the first point. And second, please be careful at the thickness of sediments. So now we can see the initial thickness of the sediments. Probably it's 5 centimeters. And but when the thrust faults and the folds are formed, the thickness of the sediment will be increased. So be careful how the sediments are thickened. And the third point, there will be some accretionary prism. That means the triangular shape of the sediment mass. And how it's important to find how the volume of the accretionary prism grow. Here I wrote the key point that the growth is self-similar. That means that the prism grow upward and simultaneously oceanward. So the prism will grow on the keeping the constant slope. Okay. So let's start the movie. あ、動かない。So now we can find some thrust faults. Next, and next, and next, next. Okay. maybe that's the end. And now we can see the triangular shape of the accretionary prism or accretionary wedge, in other words. And there are many kinds of thrust faults and folding of sediments. And probably you could see that the thrust faults are sequentially propagated oceanward. That's the typical mode of growth of accretionary structure. Okay, so I play once again. あ、いかない。So, deformation propagate oceanward sequentially. Okay? And the sediment thickness increase upward. So the slope, surface slope is kept nearly constant. That is determined by the frictional property of the sediments. Okay. And next slide is a picture of the one of the successful results. So as you saw that the thrust faults are sequentially formed oceanward, propagating oceanward. And so resultantly, the thrust sheets are stacked, resting by each other. So we call such kinds of geological structure as imbricate structure or imbricate fan. Okay, this is a typical character of accretionary complex, and the similar structure is also found in the continental collision zones, such as Himalayas and Rocky Mountains, and so on. And this is actually the compressional structure. And the second point, I already told that the growth is self-similar, both upward and both propagating oceanward, keeping the constant taper of the wedge. And there's another feature on the surface of the accretionary wedge. So you can see the narrow ridges and troughs on the surface of the accretionary complex. And if you look at carefully, you can find that the ridge corresponds to the anticline, okay, folding. And the trough is formed at the surface portion of the thrust fault, each thrust fault. So the ridge and the trough structure is formed by such compression, thrust faults and folds. Okay, and the lower right panel shows the view from the upside, and we can see the arrays of ridge and troughs. The reason why the ridges are curved, that is the effect of the friction with the glass walls. So if the wall is frictionless, the ridge should be straight. This is the effect of boundary condition. So next, we looked at the nature, natural example. Please look at this panel. Here I show the example of the Nankai Trough accretionary complex, one of the famous accretionary complex in the world. the position is here, the south central Japan. And here is the section line of the seismic profiles shown in the middle left. This is the reflective seismic profile showing the reflector of the seismic wave from the underground. So we can see the and each reflector means the bedding planes, or such strong reflector shows the upper boundary of the oceanic crust. And here is the axis of the trench. And the trench is filled with thick sediments. You can see the many bedding planes. And the sediment is as thick as 2 kilometers or more. And the trench is filled with very thick sediments. So the trench is very wide. You can see here. That is filled with sediments. So that is the reason why we don't call Nankai Trench, but we call Nankai Trough. This is a very wide depression. And in the seismic profiles, you can see some fault structure along which the sediments are thrusting up. And also we can find some anticlines and synclines, a little bit complex, but very compressive deformation structures. And the lower panels shows the interpretation of the these authors. Okay, and there are many imbricated thrust faults that is very similar to the result of sandbox experiment. And also, please look at the topographic map again. We can see the arrays of ridge and trough repeatedly occur on the landward slope of the trench. Okay, and these structures are evidently corresponding to the thrust and fold structures. And this is also the common character with the result of sandbox experiment. Okay, the ridge and trough structures. Okay, so and about 10 or 20 years ago, the researchers were thinking that these structures were formed very slowly, and there is no relationship with earthquake, because the deformed sediments are not consolidated and soft sediments are deformed. So almost all of the researchers were thinking that these thrusts and faults were formed very slowly without earthquake. But about 12 years ago, this view was changed when we Japanese have a big disaster of earthquake. So next, I talk about the earthquake and accretionary structure. Oh, probably many of participants were young when, 12 years ago, when we had a big earthquake with moment magnitude 9.0 in 2011. And at that time, not only earthquake, but very great tsunami occurred, and more than 20,000 people were lost by tsunami. Okay. And as you know, the tsunami occurs when the ocean floor, sea floor topography was greatly changed. For example, when the sea bottom were uplifted, the sea bottom also lift up the water mass. So the lifted water mass rush to the land as a tsunami. So it's very important to understand how the seafloor topography changed at the timing of the great earthquake. And in this picture, I first talk about the left panel. That is the result of the movement of GPS stations just after the earthquake and 10 days before the earthquake. And the length of arrows indicate the relative length of the distance of the displacement. And this red point is the epicenter of the big earthquake. And as you can see, almost all the GPS stations in the northeast Japan moved toward the Japan Trench or epicenter. And the maximum displacement was about 5 meters on the Pacific coast. And when I saw this result, I was very surprised because usually the big earthquake move the land only 1 or 2 meters. It's common. So 5.3 meters is quite big. But there are other geodetic stations, undersea geodetic station offshore the northeast Japan. And some of the such stations moved much more, as large as 20 meters or 50 meters. And the right panel shows this is the result of inversion model of such geodetic data. And the contours show how the seafloor or fault slipped. Okay, so on land the maximum was 5 meters, but the near the epicenter the movement was much greater, 30 meter, 40 meter, 50 meter, 6 meter, and in this model as large as 80 meter displacement occurred near the trench. And upper panel shows so I redrawn as the lower panel as the in the cross section. And here is the hypocenter, about 25 kilometers deep, 24 kilometers deep. First, the plate boundary was broken or ruptured here. And in the first 1 minute, the rupture propagated towards the down deep forward into the upper mantle. And then next 1 minute, the rupture then turned to propagate toward the surface. And after 2 minutes since the earthquake began, the rupture was thought to reach to the Japan Trench bottom. So many researchers, almost all the researchers are thinking that the fault rupture reached to the bottom of the Japan Trench here. So, and this is the site of trench accretion, okay, or accretion of sediments. And this picture shows the cross section of the Japan Trench bottom. The left-hand side is the west, and the right-hand side is the east. Okay, and the figure shows the reflective seismic profile, and you can see some bedding planes, and this strong reflector shows the upper boundary of the subducting Pacific oceanic plate. And the upper figure shows the states of seafloor before the earthquake. That was the data was acquired in 1999, so about 12 years before the earthquake. It's important that the trench floor was almost flat before the earthquake. And in the lower panel, you can see the evident uplift of or hills in the Japan Trench bottom. This data was collected just 11 days after the earthquake. It was very quick response of researchers. So it's highly probable that this uplift was formed when the earthquake occurred. Yeah. And green line is the topography or before the earthquake. The same as this topography. So the trench bottom was uplifted, and the inner trench wall or landward slope was subsided. Okay. And now we focus on this uplift part. This is the more detailed seismic cross section, and these hills were formed during the earthquake. And you can see, probably you can see the bedding planes are discontinuous across the white line. That means that these white lines are thrust faults, and sediments are displaced along the faults, and that resulted in the uplift of the sea bottom. The elevation of these hills were as high as 50 meters. Okay, and this structure is quite similar to the result of the sandbox experiment. In another word, the structure was imbrication of thrust faults. Okay, that's the common structure of the accretionary complex. So the sediment had not been accreted before the earthquake, but after the earthquake, probably after during the shaking of 2 minutes, the sediments was thrusted and uplifted. That and resulted in the accretionary structure. Okay. So now, since this earthquake, we came to think that the accretionary structures are sometimes related to the great earthquake and tsunami disaster. But such kind of seismic sounding is a sort of remote sensing, and we are geologists, and we want to see the outcrop, and until we see the outcrop, we cannot believe. So let's go to see it. Last year, I have a chance to ride on the submersible that can be go down to the bottom of the Japan Trench. This submersible vehicle is named as a limiting factor, and that is there is an American rich man bought this submersible by his money and provide for us to use as scientific use. And the submersible can go down as deep as 11,000 meters. And as you know, there is no sea bottom deeper than 11,000 meters. So we call such kind of vehicle as full depth submersible. It can go everywhere in the ocean of the Earth. And this is a self-photograph of a cockpit, and he is a pilot, Chris May, English guy, and this is me. And we are in the shell of titanium, resistance to water pressure is here. And there are 3 windows, 2 eyes and 2 mouths. So we can see, look at the outside from the window. And so when I have had this chance, I got this chance, I strongly desired to go to the this place. Yes, so I wanted to see the thrust faults. If this thrust fault is really present here or not. And this is the topographic cross section which I made during the dive. The water depth was 7,500 meters below sea surface. And the submersible landed the trench bottom here and moved to the west, this side. And fortunately, I found a big cliff as high as 25 meters. And the submersible go up the cliff and then reached to the top of the hill. And so this hill is correlated to here. Although the position of dive site and cross section is a little bit distant, but it's evident. And this upper picture is in this picture. It was taken from the submersible downward. So looking downward vertically. And here we see some garbage on the sea bottom. So we can see the vertical cliff, 7 meters high. This is a lower part of this cliff. And this picture shows the sea floor of this part. And in this steep slope, there are very numerous blocks of soft mud, comprising a terrace slope just below the vertical cliff. So it's probable that these blocks were fallen from the vertical cliff. So this is the interpretation of the thrust fault. Because the cliff was vertical, it was not the thrust fault itself. Probably the thrust fault underlies the bottom. And when the hill was elevated by the movement of the thrust fault, so there will be a hanging overhanging part at the leading edge of the thrust sheet. So this should be collapsed, and the Taylor slope probably originated from the leading edge of the thrust sheet. And the lower panel is a balanced cross section that estimates the displacement necessary to create such topography. And now I think that the lateral displacement as large as 100 meters is necessary to create such big field during the earthquake. But this is now I'm submitting the paper, and the reviewers are very critical, criticizes this interpretation. So it's still under review, and the not concrete result. Okay. So this is the, maybe this slide is the end of the first section. And do you have any questions? There are many chat describing the name of participants, so, and probably no questions so far. F22078. Do you have any question?
Ueda sensei, this is Nakamura.
Hi.
Please show some contour graph.
Okay. Geodetic data. Okay.
Okay, this is. So I'd like to know lower right part of the figure.
Here.
So, yeah. So why the amount of change, surface change at the trends larger than earthquake epicenter?
It's very good and difficult question.
Yeah.
It's evidence that the displacement is progressively larger towards the trench. And if the upper plate move parallelly slide or slide as a rigid body, the displacement should be constant everywhere. But the larger displacement in the east means that the upper plate was stretched during the earthquake. So that means that before the earthquake, the upper plate was compressed by the subducting oceanic plate. And when the plate boundary was broken, the once shrinked upper plate stretched back to recover the original shape.
Shrinking is very important.
Yeah. Please consider about the spring. When the spring is compressed or shrinked, it will store the energy, elastic energy. So during the earthquake, the energy was released. So the once shrinked spring was stretched. I think the distribution of fault displacement means the release of energy. But in the literatures, there is a few explanations of such features. So this is my idea. Okay.
Thank you very much.
Welcome. Other questions? Okay, so let's move to the next topics. So next, we'd like to see what kind of rocks are or will be accreted to form the accretionary wedge or accretionary prism. And generally speaking, the accreted materials can be divided into two categories. And one is oceanic rocks surrounded by green areas that once comprised the part of oceanic plate. Okay, so for example, the green part is oceanic crust that is composed of basalt or gabbro or such igneous rocks. And when the sea bottom is shallow, there may be some limestone or carbonates. And in the deep ocean, the chart, pelagic sediments such as chart, are settling on the sea floor. And these sediments originated from the oceanic plate itself. And the second group is terrigenous rocks. The sediments are typically turbidites, alternation of sandstone and mudstone. And such sand and mud particles derived from the upper plate as turbidity current and set on the trench bottom. So the trench bottom is still above the oceanic plate, but the sediments came from the upper plate. And the sediment and the trench sediment will be faulted and accreted as soon as it was deposited. Okay. And from the next slide, I'm going to focus on such oceanic sediments. Okay. This is what to say, schematic diagram showing the depositional setting of pelagic sediments. Okay. And probably everybody thinks that the marine is blue, but the blue ocean is comprise only very limited part of the entire ocean, because the sunlight can reach only a shallow depth as deep as 200 or at most 500 meters. And the sea deeper than 500 meters is essentially what to say, blackout, no light. Okay, and in the mid-ocean, remote from continental margins, there will be no clastic particles, terrigenous particles derived from continent. So the deposit consists essentially of biogenic materials. Okay. And especially planktons grow in the photic zone. That means the water depths where the sunlight is available for photosynthesis. Okay. So most of the planktons lives and grows and increases in the depths shallower than 200 meters. And when they are died, their skeletons or shells begins to sink down. Okay, and but in the ocean there is a special depth that is named as calcite compensation depth, or CCD, where the calcareous calcium carbonate are all dissolved out in the seawater. But not all the plankton shells is made of calcareous materials, but also there are some planktons having the shells of silica, SiO2. So the siliceous plankton shells will not dissolve so fast, so they can reach to the bottom deeper than calcite compensation depth. And in the Pacific Ocean, the CCD is lies around the depth of 4,500 or something. So and the most of the abyssal plain is deeper than 5,000 meters. So on the abyssal plain, the siliceous plankton accumulate to make a siliceous ooze, and they will be charred. Okay. And when or where the ocean bottom is shallower than CCD, not only siliceous but calcareous plankton shells can also accumulate. So and the volume of calcium carbonate is much greater than in silica, especially in the lower latitude. So there will be calcareous sediments that will be limestone. Okay. And the next slide shows representative members of planktons. And right up side panel shows calcareous planktons. One is calcareous nanoplankton or coccoliths. They are very small planktons, so we call nanoplankton, as large as several microns. And this is a phytoplankton. And the right-hand side is foraminifera. This is a zooplankton. And the size is much greater than nanoplankton. Okay. And the lower left are the siliceous members. One is diatom. This is phytoplankton. And radiolaria, that is zooplankton. These tests are made of opal, and that will be changed to quartz in sediments. And this picture is a video that is pictured at the bottom of the ocean at the depth of 3,400 meters. That is above the CCD, so the sediments are calcareous. But now I'd like to ask you to see how the plankton debris are accumulated on the sea bottom. Can you see it? Probably you can see the white particles are falling like snow. So we call them as marine snow. And they are actually amalgamates of plankton skeletons that come from the near sea surface to the deep sea bottom. And this picture shows the cross-section of sediments that is a stratified carbonate or calcareous ooze, soft sediments. Yeah. Okay. And the lower right picture shows the photograph pictured by electron microprobe. And this is sediment collected from the sea bottom near this outcrop. And you can see the very small particles, and all particles are ring-shaped. And these are all calcareous nanoplankton. So there are no sand grain and no clay, just coccolith. So the grain size is mud, but the material itself is calcareous ooze or limestone. Okay, or if semi-consolidated, we call it chalk. And this large mesh-like test is radiolaria. So this is made of silica, and the coccolith is made of calcium carbonate. So the sediment is a mixture of calcium carbonate and amorphous silica, but the amount of calcium carbonate is much greater above the CCD. So this is this will be a limestone. Okay. And these pictures show the outcrops of deep sea sediments, and upper ones are pelagic chert, and the left-hand side is radiolarian chert outcrop. Here is a very one of the most famous outcrop in Japan, in Shikoku. And you can see the bedded chart, actually alternating with silica-rich layers and clay-rich layers. Okay. And if we look at the thin sections of chart, we can find many fossils of radiolarians, and sometimes also in siliceous sponge, and also diatom in Cenozoic sediments. But this is a Mesozoic one, so the chart is composed of almost mostly of radiolarians. Okay, and the lower left picture is a bedded limestone. Actually, this is alternating beds of white limestone and gray chert. But the chert is probably a diagenetic origin. And at the timing of deposition, it was merely a bedded limestone. And I told that the limestone is actually a mixture of calcium carbonate and silica. And during the diagenesis, the calcium carbonate and silica are segregated to form such layered structure. So we sometimes call this not chert but flint. Okay, and the left, no, sorry, lower right picture shows the thin section of the deep sea limestone. So you can see some larger microfossils. In this case, this is radiolarians, and we can also find foraminifera in some samples. And the matrix is very fine-grained, muddy matrix, and but the such muddy materials are made of calcium carbonate, so we call it micrite or lime mud. And when we look at such matrix carefully, and if the preservation is good, we can see the coccoliths, that is calcareous nanoplanktons in the matrix. Yep. So in both cases, the sediments are mostly biogenic without any heterogeneous clastic particles. Okay, so the pelagic sediments and trench sediments both comprise the accretionary prism, but they form a special kind of sedimentary sequences in well-preserved accretionary complex. This picture shows the moving history of oceanic plate. Usually the oceanic plate is born at the mid-oceanic ridge as a result of volcanic activity. And sometimes the hotspot also forms a seamount as a volcanic basement. And such volcanic basements are covered by pelagic sediments because the depositional site is usually very remote from the continental margin. So only biogenic materials accumulated. And if the sea bottom is shallower, for example, on the ridge crest or at the top of seamount, the limestone will cover the basalt. But on the abyssal plain, deeper than CCD, most of the pelagic sediment might be a chert or such kind of siliceous sediments. And as the oceanic plate, once born on the mid-oceanic ridge, then moves towards the continental margin. And during the travel, pelagic sediments keep accumulated. But when the oceanic plate approaches to the continental margin, some terrigenous particles such as volcanic ash or turbidite accumulate. And such terrigenous materials will overlie the pelagic sediments because the terrigenous sediments are younger than pelagic sediments. So resultantly, the basement basalt is first overlain by pelagic sediment and then terrigenous sediments. So and this sequence is called as chart clastic sequence. That means that the chart in the lower part and terrigenous clastic sediments in the upper part. So this chart clastic sequence records the plate motion from the pelagic environment to the continental margin. So it's a very important concept that the vertical sequence is recording the horizontal movement. Okay, and we also call the chart clastic sequence as ocean plate stratigraphy. In other words, okay, that means that the sequence or stratigraphy records the history of oceanic plate. Okay. And also, it's important that we can when we reveal the oceanic plate stratigraphy, we can see, we can know the timing of accretion that is represented by the trench turbidite. Okay, because the turbidite deposited at the trench is immediately accreted just after its deposition. So the sedimentary age of the trench sediment means the timing of accretion. Okay, and the sediment just above the volcanic basement indicate the timing when the part of the oceanic crust was born at the mid-oceanic ridge or seamount, or either of volcanic activity. And it's also important that the thickness of pelagic sediments is proportional to the travel history or the duration of traveling of the oceanic plate. So if the old oceanic plate subducts, the thickness of chart is greater. And when the young oceanic plate is subducting at the continental margin, the thickness of chart or pelagic sediment is quite thin. So we can know the age of oceanic crust by the thickness of pelagic sediments or age range of the pelagic sediments. It's a very important concept. Okay. So this is the example of the geological map of the typical accretionary complex in Japan, in the Jurassic accretionary complex in central Japan. And the pink zone is chart, and the gray zones are trench sediments, such as sandstone and mudstone. And you can see that the chart and clastic sediments are repeatedly occurring, alternating. It is the very typical structure of accretionary complex. So when we consider about the result of sandbox experiments, and let's consider that such accretionary complex is eroded. Okay, at the level of this horizon, and you geologists make geological mapping from right-hand side to the left. So and when we think that this lower blue layer as chart and upper gray layer as trench sandstone. So after the thrust imbrication was formed, the sediments were thrust up along the faults, and the geologists first look at will find sandstone, and then chart, and then sandstone, and chart, and sandstone, chart, sandstone. So the sandstone and chart are repeated. And once upon a time, before the plate tectonics, geologists thought that this succession was essentially sedimentary. So geologists thought that the chart deposited after sandstone, and after then sandstone deposited, and then chart deposited, and total thickness was very big, 10,000 or 20,000 meters or even more. But after the plate tectonics was introduced to Japanese geology, we found that the all the charts were deposited at the same time. The age is identical. That was confirmed by radiolarians in 1970s or the 80s. So and now we know that all the charts originated from the same horizons, and the sandstones are also. So and the base of the chart is faulted, and so the succession was essentially apparent, and the same succession repeatedly occur because of the thrust implication. And the actual stratigraphic sequence is not so thick, limited, usually in several hundred meters or one point several kilometers. And if we carefully look at the outcrop, the base or lower margin of the chart, each chart is faulted. And the upper margin of chart is conformable boundary overlain by the clastic sediments. And it's also important that the law of superposition, that is one of the principles of geology, is not simply applicable to the accretionary complex, because all the sediments, such as chart, is frequently overlying the younger sediments, such as sandstone, bounded by faults. And it is not usually easy to find faults. So that pretend the stratigraphy. So we have to be careful at the finding the original stratigraphy in the accretionary complex. Okay. And this geological map is one of the best well-preserved parts of the accretionary complex. And but it's also common that the accretionary complex was much more disrupted. And first I have to say, explain the upper left picture. This outcrop is made of mudstone and sandstone. Brighter parts are sandstone and black parts are mudstone, and greener ones are tuff. And you see that the each sandstone body is not laterally continuous and occur as lanes or blocks. And they are embedded in mudstone. And the mudstone are black mudstone. Black mudstone are very foliated. That is actually strongly sheared. And we call such kinds of structure as melanges. That show the block-in matrix structure with shear foliations. Okay. And there are several kinds of origin of melanges. And one of the typical origin is tectonic, as pictured as this figure. So originally the sandstone and mudstone were alternating beds such as turbidite. And when the such formation underwent the layer parallel shearing, the competent layer, that is harder beds, are faulted and broken to be fragments, laterally discontinuous fragments. And softer layers will be matrix. So when the sharing is the displacement is of sharing is large enough, the originally bedded sandstones will be isolated. And if the hard bed, competed beds are composed of chart, it is the same. The block or lens will be chart embedded in softer muddy matrix. Okay, this is a we call tectonic melange. And the lower right part is a different mode, kind of melange, and that is actually a deformed conglomerate or pebbly mudstone. And in this case, the sandstone or such chart or such hard materials are deposited as sedimentary crust, and later it was they were deformed and stretched, and the muddy matrix was sheared, and we call these ones as sedimentary melanges. And it is sometimes difficult to distinguish whether the melange is tectonic or sedimentary. And if we can find some transition from non-deformed to highly deformed fabric, we can sometimes determine which of tectonic or sedimentary, but it's also common that we cannot determine the origin. Anyway, many parts of accretionary complex are disrupted to be melanges. And the lower left picture shows another part of Jurassic accretionary complex in Japan. And in this area, the sandstone, yellow one, and chart, orange one, are all not laterally continuous, fragmented. So these are actually melange in map scale. And it's important that the fabric is a kind of fractal. So the rocks are discontinuous in both in map scale and both in outcrop scale, and sometimes even in microscope scale. Okay? Melange fabric is sometimes fractal. Okay. Okay. Only 15 minutes are left. So I have to hurry up a little. But do you have any question about the lithology and the fabric of sediments? Okay. So let's move to the next topic. Now, I talked about the sediments, but then let's look at oceanic basement rocks. Okay. First, please look at the upper panel. That means that shows the topography of Northwest Pacific Ocean, and you can find Japanese island and adjacent trenches here. And the ocean bottom is not always flat, and there are some features or edifices. For example, there are some node-like features. These are called as a seamount, formed by hotspot activity. And these ridges are also formed by Hawaiian hotspot. And this is called as oceanic plateau. That this is very big basaltic volcano, flood volcano, flood basalt undersea. And there are also some island arcs such as Bonin and Mariana arcs. And these arcs are created because one oceanic plate is subducted by another oceanic plate in the ocean. So we call such a setting as intraoceanic subduction, and volcanic arc there are called as intraoceanic arc. And these are also a feature of the ocean. And in such a plate, subducted by the other plate, have back-arc basins that is opened as a result of rifting of the interoceanic island arcs. And when the island arc is splitted or rifted, it is divided into two arcs. Okay? Here, we can see here. And the arc nearer to the trench remain active, and so volcanic front here. But the other side of the arc splitted away from the trench, the volcanic activity will be stopped because the part of this arc is so remote from the trench. So we call such a deceased arc or distinct arc as remnant arcs. And both active arcs and remnant arcs are made up of arc volcanic rocks such as andesite and even with rhyolite and something dacite. And lower panel shows the schematic cross-section of such a variation in the topography and geology and magmatic activity of the ocean floor. Okay. And so there is mid-oceanic ridge and hot spot and interoceanic trench and arc, back-arc basin and remnant arcs. And the volcanic rocks there can be distinguished by each other by geochemistry. And the upper panel is an example of the accreted oceanic basement rocks such as basalt and andesite that is embedded in the accretionary complex in Hokkaido, Japan. Here's the field of my research. And even in the single accretionary complex, there are very various kinds of volcanic rocks. So, for example, we can see the such flat patterns. That means the mid-oceanic ridge basalt. So these basalts are probably accreted from the abyssal plain. But this violet one with a steep slope pattern of such elements suggests its origin from the hot spot or near ridge spot, hot spot, affected by mantle plume. So such rocks probably accreted from the subducted seamount. And brown and orange ones are rocks of island arcs. These are andesite and boninite. And so these rocks probably come from the interoceanic arc, and the occurrence of such rocks indicates that the oceanic plate was not single, because the interoceanic arc requires two oceanic plates, upper plate and lower plate, and subduction interface between. So it's important that the analysis of such accreted basement rocks helps us to reconstruct the geometry of the oceanic plate in the ancient time. Okay. Okay, these are examples of the field occurrences of such rocks. The upper left is morb, mid-oceanic rich basalt. Usually have little hyaloclastite and non-vesicular. And upper right is volcaniclastic turbidite. embedded with the chart. That means that the volcanic activity occurred in a pelagic environment. And when we analyzed this volcanic clastic turbidite, the geochemistry suggested that this is this originated from hotspot volcano. So the turbidite indicate the presence of the hotspot in the vicinity in a pelagic environment, and also the age of chart indicate the timing of volcanic activity in the ocean. And lower pictures indicate pillow lavas and volcanic clastic turbidite, debris flow of island arc origins. That is confirmed by geochemistry. And this conglomerate is intercalated within chart. So the arc was intraoceanic, not continental margin. Okay, so, and this is a concept of reconstructing the lost oceanic plate. First, please look at the upper picture. Where the oceanic ocean basins were separated by into several sectors consisting of basin 1, arc 2, this is remnant arc, and back arc basin 3, and interoceanic arc 4, and the basin 5 beyond the trench. And when the subduction proceed, the first, the basement of basin 1 will be accreted. And next, arc 2 will be accreted. And basin 3 and 4 and 5 in this order. So in the accretionary complexes, when we make geological mapping and sampling, we can determine the order of the accretion from 1 to 5. So, this order or sequence reflect the geographical distribution of basement rocks in the oceanic plate. And it's important that the oceanic plate will be subducted and lost from the surface of the Earth. So we can see them by tomography in the deep lower mantle, but we cannot touch. But when, if we make geological mapping and sampling in the accretionary complex, we can easily collect the rocks of the lost oceanic plate. It is the significance to study the oceanic basement rocks in the accretionary complex. Only 5 minutes are left. This is an example, but sorry, I have no time, and it will need much explanation, so I will skip this figure. Okay. And in the last 5 minutes, I like to talk about the basement geology of Japan. And very roughly, but this is a simplified map of the basement geology of Japan, except the Cenozoic cover sediments and younger volcanoes, and only basement rocks are shown. And also granitic intrusions are also omitted. So the map is mostly composed of accretionary complexes. It's important that the basement of the Japanese island is composed of accretionary complex, essentially. And there are so many legends, and it's hard to look at. But please find the brown ones as Paleozoic, including Paleozoic accretionary complex, mostly Carboniferous to Permian. And blue one, water blue ones, are Jurassic accretionary complex. It occupies very wide areas of the Japanese island. And green ones indicate the Cretaceous accretionary complex, and orange is Paleogene. So it's evident, especially in the southwest Japan, that the accretionary complexes of different ages form the growth zoning. That is Paleozoic accretionary complex in the north, and Jurassic in the middle, or Mesozoic in middle, and Cenozoic in the Pacific side. It's natural that because the accreted materials are transported from the ocean, so the older accretionary complex lies remote from the trench, and younger accreted materials lies near the trench. But when look at the map carefully, such growth zoning is duplicated, bounded by these red lines. Red lines, and the reason why the structure is duplicated is still under the debate, severe debate, and no concrete reasons are known. But here no time, but I introduced the basic idea that duplicated complex are not completely same, but the oceanward in the oceanward part we call outer zone. There are many fossils of tropical environments, but the inner zone, continental side, the fossils of shows more cooler, temperate environment. That means that the outer zone was drifted from the south, along with such red folds. So this is a reconstruction of inner zone in the north and outer zone originally in the south. Okay, no, only 2 minutes. And this is the final picture. This is a reconstruction model regarding the strike slip faulting that's drifted the accretionary complex in the south towards the north. Okay. Here is outer zone, and here is inner zone. Okay. So the outer zone in the south is drifted northward, and from here they are duplicated. Okay. And I forgot to explain that at that time Japan Sea was not present. And after, since the Miocene age, the Japan Sea opened since 20 million years, a little later. Okay, and opened. And this is mostly the present architecture of the Japanese island. So the basement geology of Japan is a little bit complex and still under debate, but we can explain by the strike slip movement. Okay. This is the last picture, and sorry, the time is already over. Adira, can we have time for question now?
I think you can continue.
Okay.
It's okay.
So if you have any question, please. I'm afraid that my English is not so good, so it's difficult to understand what I want to say.
Oh, it was clear.
Clear, thank you. Thank you. Oh.
Okay, if there are no questions, means we will. You have anything to add? Ueda-san, you have anything to add here as concluding remarks?
Okay. For me, that's enough, and a little bit tired.
Okay.
Thank you.
Okay, Ueda-san, thank you very much.
Thank you
For your wonderful lecture. It was really interesting. I'm sure everyone enjoyed today's lecture.